Hi everyone. So today I want to tell you about quantum orchestration for quantum error correction. And I really hope to show you that the quantum orchestration platform that we're developing at Quantum Machines allows very fast and very flexible development of quantum error correction protocols from a very intuitive software interface while not compromising on the real-time hardware capabilities that are required, in fact, for quantum error correction. And in fact, pushing these real-time hardware capabilities to record performance that is available today in the field. All right, so starting from the sort of broader context, we believe we're seeing today in quantum computing two very critical parallel efforts that are going on that I will call the two races of quantum computing. The first race is the race towards quantum practicality, and this is about demonstrating the real-world value of quantum computers as soon as possible on NISQ devices, of course. And this is very important in order to push the field forward and, of course, to ensure that we continue to have more and more resources directed towards quantum computing. And then the second race is the race towards fault-tolerant quantum computers. And this is about demonstrating or implementing quantum error correction protocols to successfully deal with the high level of noise or the high error rate that exists in today's quantum computers. And this is, of course, super important because this is what will allow us to eventually realize the full-blown potential of quantum computers. So at Quantum Machines, we're actually pushing these in these two directions very, very strongly. In the two talks that we gave in this year's Q2B, which, by the way, let me say it was an amazing conference, and I want to thank the organizers for really doing an amazing job setting this conference up and bringing everyone together. So really, thank you. And so we at Quantum Machines, in this conference, we've really stressed the importance of the integration between classical and quantum and pushing this integration much, much more to the limit, as well as integrating quantum computers and quantum machines in heterogeneous compute environments. And we've looked at how we can achieve this with our unique pulse processor architecture, unique pulse processor approach, the pulse processor that brings real-time classical processing into the control layer of the quantum computer, the quantum controller, as well as the integration that we're pushing more and more of the quantum control layer with the more general classical compute power. So we have the QPU there, then we have the pulse processor which brings real-time classical processing, and then the more general classical processing resources like CPU, GPU. And so today I want to focus how this approach, and in particular the pulse processor with its real-time capabilities, how it will allow us to run much faster in this second race right here, the race towards fault-tolerant quantum computers. And I think the word race here is actually very appropriate because we want to maximize how fast we make progress with quantum error correction. And this is because there are subtle technicalities that make developing quantum error correction actually very, very challenging. So first, on one hand, you need to have these real-time control capabilities that I mentioned. We need to actually orchestrate quantum and classical operations together, interleaved with very, very precise control over timing on the nanosecond scale and with feedback latencies that can push down to hundreds of nanoseconds. And on the other hand, there's a long way to go. That means that we need to, there's so much more learning and exploration that needs to be done in order to understand how we should really run quantum error correction protocols. And so it's not enough to build systems or specific hardware that will optimize performance, but will be very limited to a single quantum error correction protocol or a single variation of it. Instead, we really want to maximize this learning cycle of keep coming up with new ideas, implementing them, and learning from them. And so it's very important to build very flexible systems that on the one hand give us the flexibility to program these demanding protocols from software, and on the other hand give us the hardware capabilities. And this is exactly what the quantum orchestration platform comes here to do. So before I tell you about the quantum orchestration platform and show you some examples of how we can code quantum error correcting codes with it, let's first take a step back and talk a little bit about quantum error correction. So if we look at classical computers, they don't typically make any mistakes, right? So if we ask a classical computer, what are the prime factors of 15, it will tell us pretty much for sure that it's 3 and 5. So there's an algorithm to do it. Of course, it's not the most efficient algorithm, but there is an algorithm to do it, and it will give us the right answer. So classical computers don't make mistakes, at least almost. So every now and then you get the blue screen of death, of course, and actually I've heard that whenever you get the blue screen of death, there's a high probability that it actually happened because of an exotic event like a cosmic ray that actually hits your computer and causes this error. But it happens very rarely, right? Not often we have cosmic rays causing errors in our computers or our cell phones. So today we're at, very low error rates with classical computing today. The problem with quantum computers is that quantum bits, qubits, are very, very sensitive to noise from the environment. So basically, not just cosmic rays could cause errors, but many other things could cause errors in our qubits. And so today we're down at about the 10 to the minus 3 level of errors in most quantum computing platforms. And there are actually two kinds of errors that could happen. We can have a bit flip where a 0 turns to a 1, and we can have what's called a phase flip where a plus in a superposition becomes a minus. And so this is the main problem, in fact, with performance of quantum computers today. And quantum error correction tries to deal with it, tries to solve this problem of errors. And it does that by using a system with a redundancy of qubits or redundancy of quantum states together with classical control and compute power, classical control and compute power, in order to encode quantum information in what's called logical qubits that are protected from these errors. Okay, so quantum error correction protects quantum information by storing it non-locally in correlations over many physical qubits. So this is a complicated sentence, but we can see what it means by looking at a simple example. So if we look here on the left, we see how we typically encode information on physical qubits. So we actually encode these two numbers here, alpha 0 and alpha 1, by a superposition of a single physical qubit. So alpha 0 times the 0 state plus alpha 1 times the 1 state. But we can change that. We can encode the information in a state of 3 qubits, for example. So we save the same, exactly the same two numbers, alpha 0 and alpha 1, but now in a superposition of these 3 qubits. So alpha 0 times 0, 0, 0 plus alpha 1 times 1, 1, 1. And then we can see that even if there is an error, let's say the third qubit got flipped because of some event, we can actually recover the errors, because you see most of the qubits here are still in the correct state. The problem is we cannot just simply measure the qubits, because if we measure the qubits to do a majority vote, we will collapse the state of the qubits and lose the information. Instead, you need to have a control agent which is slightly smarter than that, and it will perform clever measurements to discover the errors. In this case, it's actually pretty easy to do that by measuring the parities of pairs of qubits here. So we measure if the first and second qubits are the same. This is called the parity of the first and second qubits, and then we measure the parity between the second and third qubit. And from these measurements, we can infer the error. So for example, in this case, before the error, the two parities were even, and after the error, we have even and odd. Okay, so these pairs of parities here are called the syndrome measurement. And by measuring the syndrome over and over, we can actually infer the errors. So we start from even, then we move to even odd, then odd, odd, and so on. And we can infer the errors. But this is actually very hard, okay? In fact, it requires a combination of having great physical qubits, great gate fidelities. like the operations that we perform on the qubits need to be very accurate, and real-time control. So even the least demanding quantum error correction protocols require error rates, physical error rates before the error correction of below 10 to the minus 2. And these least demanding protocols in terms of the physical error rates are actually very demanding in terms of the number of qubits and in terms of the real-time control that we need to do there. So we really need to balance these two things, and it's actually very, very hard. At QM, we actually just know how hard it is because very proudly, the first demonstration ever of quantum error correction was actually performed by no other than our chief engineer and one of the co-founders of the company, Nissim Ofek. And you can see here in this picture just how complicated it is to run the first demonstration of quantum error correction, which was a single logical qubit, not even performing 2-qubit gates, not even scaling up. And you can see this very complicated control flow diagram of the experiment. And another thing to mention here is that when they developed it, they had to do many different things, different tricks, different variations of the algorithm. So it's not enough just to build a hardware that can implement this specific protocol. You have to build something that's flexible enough so that you can change the protocol easily and rerun it with high performance. And that's what we're doing at Quantum Machines. Our mission is to bring the best out of any QPU, bring the best performance out of the hardware, and then achieve the fastest time to results. Okay, so providing a platform that allows you to easily program these protocols and still get the best out of your hardware. So here are the components of the quantum orchestration platform. We have in our hardware the very scalable and very modular analog front-end that allows to produce the control signals that achieve the gate fidelities, the best gate fidelities that are available today in the field. And then the heart of the technology, which is our pulse processor. This is a real-time processor that is sequencing the entire quantum program. So that includes generating the pulses, performing the measurement on the QPU, the quantum processor, and also bringing the classical compute resources that run in real time and the control flow into this game. And the interface to this pulse processor is our very intuitive, very powerful programming language, QA. And this is a first of its kind programming language because it really allows you to interleave quantum and classical commands in the same code, okay, and run them, sequence them with nanosecond scale precision in terms of timing, and run them on the hardware, on the pulse processor. Okay, beyond QA and the pulse processor, we've also integrated into our hardware many good things like coprocessors, stream processing, high bandwidth networking, storage, and now we're implementing caching in order to push this integration with classical resources, general classical resources, as I mentioned, to the limit. And above that, we have our control software where we are integrating with higher level components in the stack. For example, we have our new integration with OpenChasm, which we're going to release early 2022. And then our open source entropy platform for calibration automation and QPU abstraction and all the open source libraries we're developing together with our customers today. Okay, but today I want to focus on QA and the pulse processor because this is really what allows us to write, to program quantum error correction codes very easily and flexibly and run them with the best performance. So it's really this combination of QA and the pulse processor. So let's look a little bit about QA and how it looks like. So the first thing we have in QA is the basic quantum operation commands that are the play and measure commands. So actually, this is a pulse level language. So we're talking in terms of the pulses that we need to send to these qubits to perform the operations. So we can send pulses to the qubits with these play commands. I play a pi pulse, for example, to qubit 1 here. And then the measure command that allows me to measure signals coming back from the quantum processor or measure different elements on the quantum chip. And then we have classical processing. So we can define general classical variables, and we can perform general classical operations on them, like A equals B squared plus 5 here, okay? And they can actually affect one another. So for example, I could use these classical variables to affect parameters of the pulses that I'm sending to my qubits. So play pi pulse times amplitude A. So I'm changing the amplitude or parameter of the pulse with these classical variables, or the duration of a pulse, and so on and so forth. The next important feature that's very critical, and it's going to be very critical for quantum error correction, of course, is that the measurements could actually feed these classical variables. So I could measure, for example, a resonator on my chip, and then the result of this measurement goes into this variable I here. And I can then further process this variable. So I can say state, which is a Boolean variable, equals I larger than 0.012, okay? This is state discrimination, for instance, to estimate the state of my qubit. And then I could do control flow. So I could say, for instance, if I'm in the excited state, I want to play a pulse to my qubit, or while I'm measuring some error syndrome, I want to do something. Okay, this is actually very relevant in quantum error correction, as we'll see. And so you program very intuitively like this, because classical variables can affect control flow, affect parameters of pulses, and could be fed by measurements. And finally, we have complete timing control, both relative to a global timestamp, of course, but also with multi-threading, we can synchronize and asynchronize different threads that live in the pulse processor. Okay, so I want to look now on several examples of quantum error corrections and how we can implement those in QA. So first we'll look at the repetition code that's similar to what Google ran in their recent publication from July 2021. Then I want to look at the magic state preparation a la AWS, the proposal that came out at the end of 2020 to do error correction with CAT codes. And finally, look at the adaptive error syndrome measurements a la Honeywell, or should I maybe now say Continuum. And so these are the examples we'll look at. Okay, so first, the repetition code. So this is also the prototype of the surface code. So they're kind of like similar in the way we run things. So here is actually the simplest repetition code. It only requires 3 data qubits. So it can only correct for a single bit flip error. It can actually not correct for even a phase error. And it uses 3 qubits for data, and then another 2 qubits for what's called ancilla qubits, or measurement qubits. You use these extra qubits to perform the parity measurements I mentioned. And so even in this simple example, we already see all the demanding parts of quantum error correction. So what do we see here? We see first mid-circuit measurements, and then we see error tracking or error decoding that needs to happen in real time. And then we need to run it many times. So you see these times end there, because we want to track errors many times to do fault-tolerant quantum computing. And then many times we want to reset the ancilla qubits every cycle of the measurement, every cycle of the error correction cycle. And this requires fast feedback based on the states that we measured the ancillas before, to reset them back to the ground state. And finally, at the end, we need more feedback because we need to correct for the right errors. So we track the errors, and then before we want to use that qubit, we want to measure the data, we want to correct. So here's the QA code used for the repetition code. This is just for the tracking part. You see here the C naughts at the beginning and the measure states. These are QA macros that are actually defined elsewhere. And so they define the path sequences for all of these operations. And then you can see the second part there, which is actually the classical processing part of the tracking. So we simply, we very intuitively program it. We measure the ancilla in the measure states there, and then we perform the classical processing. Basically, based on the ancilla measurements that we performed, we set the values of this, what I called here, flips vector, which tracks the errors. So which of the 3 data qubits flipped. And I can add the error correction at the end. Actually, in the Google paper, this was not done because they did not have feedback in their control layer. And we can do that. We can implement easily, as you can see here, the feedback operations, and this will run actually with the best performance that's achievable today of about 200 nanosecond latencies. Yeah, and then in the same way, you see how I can easily add commands. I can add the resetting of the ancillas, just add play commands whenever is needed based on the ancilla states. And again, this becomes now very demanding because I want to correct every cycle for the ancilla states. And I can do even more. We are now at QM, we're developing more complicated protocols that use real-time control to adapt the error syndrome measurement itself in real time based on the error tracking in order to improve the measurement fidelities as well as reduce the cycle time. I won't talk too much about this except saying that we hope to publish some more interesting stuff about this in the following months. But you can see you can really easily implement things like that in QA. And again, it will run on the pulse processor in real time with highest performance. So this is the repetition code. Next, let's look at magic state preparation. So this was the proposal from AWS that allows to do fault-tolerant quantum computing with concatenated cat codes. So these are states encoded in bosonic modes and cavities. This is actually sort of like the continuation of what Nissim did during his postdoc at Yale. He was like this first demonstration that I showed you before of quantum error correction was in fact based on cat qubits encoding, so states, quantum states that are encoded in bosonic modes of cavities. And here on the right, you see the pseudocode that is suggested for what's called the easy stop algorithm that they suggested to prepare magic states. Magic states are important when you want to apply operations to your corrected qubits, to logical qubits. So we won't go deeply into this. I just want to show you the QA code here, which actually really resembles the pseudocode. So this is how you would write this thing in QA. Simply, so here's the while loop, and then the if statement with the classical assignment there, the measurements, then the classical processing with the control flow, etc. So I think even in terms of number of lines of codes, this is almost the same. And so we've implemented this and we've actually benchmarked it. And there are actually more ideas of how we can push forward this magic set preparations with QA and with the pulse processor to get best performance. And finally, the adaptive error syndrome measurements by Honeywell. So this is a super impressive, super complicated experiment that I think is really nice to do fault tolerant, really including correcting of the errors. We've implemented this in QA. Again, I won't go deeply into this. I'll just mention that you can see all the parts here. You can see the repeat until success here, and then the logical operation that depends on the current state, and then the quantum error correction cycles, including a very demanding control flow that, again, adapts the measurements in real time, and then the final stage there of actually performing the logical operation based on the measurements, and then correcting classically for the errors. So we can do that with QA. Now with trapped ions, actually, I would say that this is interesting because yes, thank you, almost done. So I'll just say that with trapped ions, it's kind of like it seems maybe easier to do quantum error correction because the timescales are so much longer. But then what we think is that we do need to push classical processing to its limit in terms of timing and real time, because the more you can do, the more you will do. Quantum error correction is a really difficult task, and in fact, I'm sure that even in trapped ions, people are trying to shorten the gate time. So the shortest gate, the shorter the gate times will become, the more demanding demands you will have on the control. So you will need these real-time capabilities, and you will need again to program them from software. All right, so I hope I convince you that with QA and the pulse processor, you can really program quantum error correction intuitively without compromising on real-time performance. I'll just mention very briefly that the other things that we've implemented that integrates classical processing are also important, because coprocessor could be important later on as scale of quantum error correction increases, and we need more processing power in our control layer, as well as streaming capabilities, because at least in some platform, one could think about sending the data to something like a high-performance computer that will allow better to do the error tracking as we keep measuring these qubits. So again, I hope I convince you that the quantum orchestration platform really enables R&D with quantum error correction with unprecedented performance and allowing to achieve fastest time to results. So let me thank you, and I think I have a few minutes for questions. Thanks. Yes. Okay. I don't know,
there's a mic here. If you want to, you can take this mic and go ahead.
All right. Thank you for a very nice talk. So it looks easy with the while loop repeating itself. But how fast is it? I mean, what is the typical, in these examples you showed, the typical time for one while loop to execute?
Yes, so it's typically on the order of between 200 and 400 nanoseconds, depending exactly, of course, on the calculations that you want. Yes, one loop.
Including measuring?
No, not including, well, I mean, I'm just talking about the feedback part, because of course the entire loop will depend on the gates, the duration of the gates, and that will depend, of course, on your quantum processor.
For these concrete examples?
So for the repetition code, we took, for example, the same, same pulses that Google have used in their paper, and then I believe that the entire cycle time takes about a microsecond, something like 1.4 microsecond, something like that, if I remember correctly. Yes. And the nice thing is that even if you push things down to like a microsecond, we can still do the feedback, which will be negligible compared to that. So for example, for resetting the qubits or for doing these adaptive error syndrome measurements, in fact, we think that we can enable getting rid of the reset part because of the adaptive error correction, error syndrome measurements. Yes. Sorry. Yeah.
Sometimes when we read out an error syndrome, we're more confident in the result from the signal than other times. You can assign a probability to 0 and 1 rather
Yes.
than a hard interpretation of the signal, and then do a soft decoding.
Yes.
So can your software do this?
Yes, actually, that's. I'm glad you brought that up, because that's one of the things that I think that we do. So you saw that there that we can do analog. You saw, maybe I can even go to this example. So let me go back to QA, like what I showed about QA. So you see here in this example, we measure, for example, a resonator, and this result I is an analog value. It's not, we don't measure like 0 or 1, right? So we just measure, for example, the quadratures coming back from the resonator. Here I'm doing a, like a sharp state discrimination, right? But I could define any classical variables. I could define a vector that holds the probability distribution, and I could update this, like I could do Bayesian updates. We've done that with some of our customers. Actually, not in the context of quantum error correction, in the context of quantum sensing, but this is bread and butter for the system. So, yeah.
All right, we have time for one more question. Yes.
Try to cheat math too. So the first thing is a little bit of confusion. You were very specific in the Google case of talking about bit flip errors, but not phase flip errors. Mm-hmm. And then you were less explicit in the later portions, at least to my hearing, about what types of errors you were considering correcting. Are you ambitious enough to try to tackle multiple different types of errors simultaneously? That's the first question.
Yes, for sure. I mean, we've implemented like surface, I just wanted it for the example to be simple, but we've implemented surface codes, we've implemented magic state distillation. So a surface code would correct for both bit flip and phase flip error.
Yeah, but there are other more complicated errors that could also come up, right? So is the system designed to scale to?
Oh, yeah. In fact, like, so, exactly. So, like this, for example, could take into account, these adaptive error syndrome measurements, for example, would take into account measurement error. They would actually reduce the overhead that you would have to do in order to track both measurement qubit errors as well as data qubit errors. Sorry?
Because you're sharing.
Yeah, we're also sharing information across the entire system. So you can connect many pulse processors together, and they share data in real time with an overhead of about 100 nanoseconds to transfer like a 32-bit word from one processor to another.
Second question might be a little bit easier. And that is the definition of real time varies in the trade. Okay. So there are safety critical systems that continue to operate even when a programming error on the classical side takes place. Mm-hmm. And there are soft real time, which have some vague guarantees about how long before you get a response back. So what are you doing in the way of real time? Which type?
So real time means, at least in our case, that the quantum operations that you're performing, they are guaranteed to happen in a specific times relative to the global timestamp, up to, of course, if you have control flow. So, for example, if like like you're branching the program based on a measurement, but even that will be deterministic. So the latency will be deterministic. Okay, so everything is fully deterministic on a nanosecond scale. In fact, on a picosecond scale. And now with classical errors, they happen much. We do classical error tracking. But we don't do, for example, retransmits of signals from, for example, one place to another because we don't want to hurt the real-time quantum operations that have to happen. And we think that's actually important because you don't get that many classical errors as much as you get quantum errors, so that's not a big, something big to pay. Yeah.
All right. Well, thank you, Yonatan. Let's give him a hand one time.
Thank you.